Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. The first two layers of the OSI model, Layer 1 and Layer 2, form the foundation of all network communication. These lower layers handle the core functions that enable devices to transmit and receive data, making them absolutely essential to every aspect of networking. At Layer 1, we deal with the physical transmission of electrical, optical, or wireless signals. At Layer 2, we manage the logical link between devices, framing that raw signal into a format that can be understood, verified, and forwarded. Together, these layers establish connectivity and prepare data for movement through the rest of the OSI stack. Understanding Layers 1 and 2 is critical for anyone pursuing the Network Plus certification because they represent the starting point for every bit of data that enters or leaves a device. These layers are responsible for the movement of signals and frames, supporting all upper layer processes. When troubleshooting connectivity issues or configuring devices, insight into these lower layers helps determine whether problems lie in the cable, the signal, the interface, or the address resolution. They are the base of the data path and cannot be overlooked. Layer 1, the physical layer, is responsible for transmitting raw bits across a medium. It converts binary ones and zeros into electrical pulses, light pulses, or radio waves depending on the media type. This layer defines the physical aspects of network connections, such as the layout of pins in a connector, the voltage levels used to represent bits, and the type of cabling required. Layer 1 does not care what the data means. It simply ensures that it can be physically sent from one device to another. Physical media, such as copper, fiber, and wireless, each have distinct properties that influence how signals behave. Copper cabling relies on electrical signals, and its performance can be affected by distance and electromagnetic interference. Fiber optic cable carries data using light and can support longer distances and higher bandwidths without degradation. Wireless media transmit data using radio frequencies and are more susceptible to environmental interference, but offer flexibility and mobility. Understanding these characteristics helps you select appropriate media for different environments and applications. Many components in a network operate entirely at the physical layer. These include the cables that connect systems, the connectors and jacks that secure those cables, and the patch panels used for organizing and extending connections. Devices like hubs and repeaters also function at this layer. Repeaters regenerate weak signals to extend transmission range, while hubs broadcast signals to all connected devices without interpreting the data. Although modern networks often use switches instead, these components still appear in legacy systems and exam scenarios. At Layer 2, the data link layer introduces structure and intelligence to the raw signal by forming a logical link between directly connected devices. This layer is responsible for framing, which involves taking network layer data and wrapping it in headers and trailers to create a frame. These frames contain not just the data payload, but also information for destination and source addresses, error checking, and flow control. Framing turns a stream of bits into a meaningful data unit. One of the key features of Layer 2 is addressing. This layer uses Media Access Control, or MAC, addresses to identify devices within a local network. A MAC address is a unique identifier burned into the network interface card of a device. Unlike IP addresses, MAC addresses do not change and are tied to the physical hardware. Layer 2 communication depends on these addresses to determine where to send frames on a network segment. This is essential for functions like Ethernet communication, where accurate device identification ensures proper delivery. Switches are the most common Layer 2 devices, and understanding their operation is crucial for the exam. Switches read the destination MAC address of incoming frames and use MAC address tables to determine the correct output port. This allows them to forward frames only to the intended recipient, improving network efficiency compared to hubs. Switches build their tables by learning which MAC addresses are associated with which ports, enabling intelligent forwarding decisions that reduce unnecessary traffic. Frames at Layer 2 are built with specific structure. Each frame includes a header that contains source and destination MAC addresses, along with other metadata like frame type. The trailer typically contains error-checking bits, such as cyclic redundancy check values. Start and end delimiters mark the boundaries of the frame to ensure it's properly recognized. This format encapsulates data from the network layer, providing the structure required to transport it reliably over the local network. Error detection and flow control are essential responsibilities of the data link layer. Techniques like parity checks and cyclic redundancy checks, CRC, allow receiving devices to detect transmission errors and discard corrupted frames. Acknowledgement systems confirm that frames have been received, and flow control prevents fast-sending devices from overwhelming slower receivers. These methods improve reliability and ensure that even basic frame-level communication is stable and verifiable across the link. Layer 2 is further divided into two functional sublayers, each with its own responsibilities. The Logical Link Control, or LLC, sublayer manages communication between the network and data link layers, handles error checking, and sometimes provides frame sequencing. The Media Access Control, or MAC, sublayer handles physical addressing and controls how devices access the transmission medium. This separation supports modular design and allows different technologies to share the same overall structure while adapting to specific media requirements. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. Layer 1 and Layer 2 serve very different functions, and understanding their distinctions helps clarify their individual contributions to network communication. Layer 1 handles the physical movement of raw bits. It transmits signals but does not interpret them. In contrast, Layer 2 manages logical communication between devices by organizing those bits into structured frames. The difference is often described as signal visibility versus data awareness. Layer 1 is passive, it carries data, while Layer 2 is intelligent, making decisions based on addresses and control information. Standardization is vital at both layers, ensuring that devices from different vendors can operate together reliably. Organizations such as the IEEE create standards that define behavior for these layers, including the widely known 802 series. For example, 802.3 governs Ethernet, while 802.11 defines wireless communication. These standards establish a common framework so that equipment can be built to a consistent specification. This enables plug-and-play compatibility, facilitates troubleshooting, and ensures that physical and data link communication behaves as expected in multi-vendor environments. Layer 2 communication is typically limited to the local network segment or broadcast domain. Switches forward frames within a single local area network, but they do not route traffic across different networks. As a result, Layer 2 devices are unaware of IP addresses and cannot reach external networks on their own. This boundary defines the role of switches and highlights the need for Layer 3 routing devices when internet communication is required. Understanding the scope of Layer 2 helps clarify how and where certain devices operate in the OSI model. Physical layer has its own set of limitations, especially when it comes to signal integrity and distance. Copper cables are subject to attenuation, where signals weaken over long runs, and are also vulnerable to electromagnetic interference from nearby devices or cables. Fiber optics offer greater distance and immunity to interference, but they require more precise installation. Wireless transmission can be disrupted by walls, metal objects, and competing signals. Recognizing these limitations helps you anticipate connectivity problems and choose appropriate media for a given environment. Layer 2 supports three major modes of data transmission: unicast, multicast, and broadcast. In unicast, data is sent from one device to a single specific recipient. Multicast allows one device to send data to a defined group of devices that have expressed interest in receiving it. Broadcast sends data to all devices on the network segment, whether they requested it or not. Ethernet and Wi-Fi both support these transmission types, and understanding how they are used helps explain how traffic behaves within a local network. Duplex and speed settings are key to maintaining stable network links. Half duplex allows devices to send or receive data but not at the same time, which can lead to collisions in older Ethernet networks. Full duplex supports simultaneous sending and receiving, eliminating collisions and improving throughput. Speed negotiation allows devices to automatically select the highest supported transmission rate for both ends of a link. If settings are mismatched, connections may drop or perform poorly, making duplex and speed parameters vital for troubleshooting. Link establishment involves a handshake process where devices agree on parameters before data transmission begins. This may include negotiation of speed, duplex, and signal type. Many modern devices use auto MDIX features to automatically detect and adjust for cable types, eliminating the need for crossover cables. Carrier sense and link detection confirm the physical presence of a signal, enabling the interfaces to activate. This entire process happens at Layer 1 and Layer 2 before any IP communication begins, showing how foundational these layers truly are. From an exam perspective, questions often require you to identify which OSI layer a device or issue belongs to. You may be asked whether a problem with a cable is a Layer 1 issue or whether a switch's forwarding decision is a Layer 2 behavior. You'll also need to recognize the differences between frames and signals and understand which layer manages each. These distinctions appear frequently in Network Plus questions, and being able to confidently categorize tasks and devices by layer improves accuracy and helps you approach scenarios with greater clarity. Layers 1 and 2 together provide the foundation for all network operations. Layer 1 delivers the physical movement of signals through various media, while Layer 2 shapes those signals into frames, assigns local addresses, and manages the flow of traffic. These layers work together to support local network communication, forming the base upon which all upper layer processes rely. Without them, no network transmission could begin, making their understanding essential for both certification and real-world success. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.